Yes, good morning, sir. Welcome back.
Good morning, sir.
Sir, it's audible to you?
Yes, no problems.
1 minute, sir. Okay. 1 minute, sir. Okay. Yes, sir, it's now audible?
Yeah.
Okay. So there is a wrong selection for my speaker
Okay.
because microphone also got connected. Sorry, the headphone also got connected.
Mhm.
Yes, sir. Video on, sir. So another one also your mobile, Aishwarya?
No,
No.
not mine.
Okay. Maybe some student.
Okay. Had breakfast, sir?
Yes, sir. Done, sir. Maybe 5 minutes, sir. They will join.
Yeah,
Once
fine.
few students join, then I will leave the meeting. You can take the
Sure.
full control.
Sure.
Yes, good morning everyone. Welcome back. Hope my voice audible. Yes, Guwahati audible, right? Shivakiran audible, right?
Yes, sir.
Surinder, you can confirm. Febin? Okay. Okay. Fine, Febin. Yes, Praneeth, welcome. Audible, Praneeth? Please confirm.
Yes, sir. Audible, sir.
Okay, Praneeth. Yes, sir, we can begin, sir. So you can turn on the mic and also the video. Yes, sir.
Yeah. Hello, good morning, everybody. Am I audible? Am I audible, everybody? Clear?
Yes, sir.
Yeah, thank you. So myself, Chandru. So today we'll talk about heat transfer subject. Let us see the things. Let me share my screen. I think, sir, we need to give a permission.
1 minute, sir. You can turn on the video also, sir.
Ah,
1 minute. Yes, the control is given, sir.
yes,
Okay. You can accept and share the screen.
I'll go with turning off video only. Like that will be comfortable for me. So are you able to see the screen which I have shared just now? Everybody, are you able to see the screen? Is it visible?
Yes, sir.
Yeah, thank you. So let us start with the new subject. I think it's let us assume that it's new for you guys. Don't think like that's something you have learned in your academics and all. Let us start as a fresh. So coming to the syllabus point of view, yeah. Let me give you the syllabus, the broad syllabus. So coming to the syllabus point of view, so we'll divide the entire syllabus sheet of heat transfer into four parts mainly. One is conduction, followed by convection, followed by heat exchangers, then finally radiation. Then finally radiation. So if you see the entire syllabus sheet, whatever they have given under heat transfer, whatever they have given under heat transfer, we'll take into 4 parts. One is conduction, followed by convection, heat exchangers, then finally radiation. So if you see the gate point of view, you will be getting around 4 to 5 marks. This is the weightage of the subject, which is 4 to 5 marks. So if you see in your mechanical syllabus sheet, this will be weighted after your fluid mechanics and strength of materials. Fluid mechanics and strength of materials will be 6 to 7 marks. After that, the most weighted subject is heat transfer. Say starting from production, we have some weighted around 20, then followed by your mathematics around 15 marks, then followed by thermodynamics, which is around 10 to 12 marks, then fluid mechanics and strength of materials 6 to 7, 6 to 7. Then the next most weighted subject is heat transfer. So why we give the weightage means you need to spend time based on the weightage. That's how I prefer a given subject. If a given subject is having more weightage, you can you need to spend more time so that you should be greedy in scoring the marks. More weighted subject means more spend you need to time while preparation, and more time you need to spend while solving problems, practicing, or whatever may be. Try to get as much as marks as possible. That's it. That's the entire goal of a given weightage for a given subject. So coming to the textbooks. The first one, please try to follow these textbooks only. These are very good textbooks. Heat and mass transfer by Incropera. And second one, heat transfer by Sengel. And the third one, Holman. Heat transfer by Holman. So try to follow these textbooks only. Don't follow any local authors, because what I observed from the previous questions is people are setting the questions following these textbooks, and that means how I can say that statement means they're simply taking the same questions from these textbooks with changing the numbers. That means the type of problems you see in gate questions, they're simply copied from these textbooks. You can observe similar kind of questions from these textbooks.
A small
That's
interruption.
what I felt after reading these textbooks. Yes, sir.
Small interruption, sir. So we can admit the students, they are waiting.
Yeah.
Some students are waiting.
Oh, yeah. So admit all.
Fine, sir.
Yeah, thank you, sir. So now, if you see these textbooks and compare with your previous questions, you'll see most of the questions, they are simply taken from these textbooks just with the change of numbers. So that's why I always prefer or ask my students start reading these textbooks while you are preparing for a subject like heat transfer, so that it will be helpful for you guys when you go for directly in the exam. You will not feel that question is new for you. You will feel that already you might have seen that question somewhere else or solved somewhere else. So that you will see from these textbooks. So that's what the importance of these textbooks. So please be careful. So these are very, very good textbooks if you want to learn the fundamentals or applications of heat transfer. Very good textbooks. Incropera, Sengel, and Holman. Even I prefer for teaching also these textbooks. And the next one, you can follow NPTEL videos by Professor Suman Chakravarti and Professor S.K. Som from IIT KGP. So if you have any queries in terms of learning or whatever maybe, you can watch the videos of these professors. They are from IIT Kharagpur. These videos are available in the YouTube. You can follow those videos also. Apart from reading the textbooks and learning from the classes, you can simply watch their videos also. Is it fine in terms of any questions in terms of syllabus, textbooks, and all those things? Any doubt? Clear? So if it is clear, let us try to learn first fundamentals before going for the actual chapters like conduction, convection, heat exchangers, and radiation. Let us see some basic fundamentals before going for actual subject. So let us see the topic name, which is heat transfer. It is heat transfer. Heat transfer. Let us try to learn some fundamentals from here. Then go for the actual subject, like in the name of chapters. So the first question we should answer before going for the actual subject is, what is heat transfer? Why you are going to read a subject like heat transfer being a mechanical engineer? What's the purpose of this subject? Where you will see the subject in reality. So these type of questions first we have to answer. Then we can go for learning the things. So I prefer not only for this subject, any subject you take, first try to ask this question on yourself, saying that why you want to read, what's the purpose. Don't think about marks and all, leave about marks. First let us see where you will see this kind of subject in real application. Being an engineer, you should know the applications of a given subject. Right? I think you might have heard the similar kind of term in a subject like thermodynamics. Is it right? Everybody clear? You might have heard a term like heat transfer with a symbol, or notation as Q, right? As Q in a subject like thermodynamics. You might have seen the similar kind of term there also. In every part of thermodynamics, in each and every class of thermodynamics, you might have learned, you might have seen very regularly a term called heat transfer, denoted with Q. A similar kind of term we are going to read as a subject, which is called as heat transfer. The subject name itself now is a heat transfer. And one more thing you should be very clear here is, in thermodynamics, you know how to evaluate the value of Q. In thermodynamics subject, you know how to evaluate the value of Q for a given process or for a given cycle or whatever may be. You might have learned some techniques. How to calculate the value of Q. Broadly speaking, the units of Q in thermodynamics was joules or joule per kg.
Kilojoule per kg, no, sir.
Joules, yeah, kilojoule per kg doesn't matter, right? That's just a division of 1000.
Q is energy, no, sir.
Okay?
Energy transferred or heat.
Yeah, correct.
Q is energy.
Yeah.
In this case, heat energy.
Yes, correct. Heat, work, these are all different forms of energies, that's it. But general units in your thermodynamics for this heat transfer is joules or joule per kg. Is it okay, everybody? So joules means Newton meter. Is it correct? Joules means Newton meter. Kilojoules means it's just a conversion from joules to kilojoules by dividing with 1000. That's not our intention here. Our intention is broadly seeing how you are going to represent Q in a subject like thermodynamics, means that is joules or joule per kg. Whereas in thermodynamics, nowhere you talked about how to design a given surface. Whenever you want to talk about a heat transfer, you didn't talk about what are the areas available, what are the dimensions available for a given surface to talk about heat transfer in a subject like thermodynamics. Our interest was not that in those kind of phenomena. In thermodynamics, our interest was to calculate mainly how to convert one form of energy into another form. Is it right? In thermodynamics, our interest was to convert one form of energy into another form. Or the second one is how to apply the energy concept on different cycles, right? Like power plants, gas power plants, steam power plants, refrigeration, air conditioning. In all these different kinds of applications, in these kind of applications, you applied like how to convert one form of energy into another form, say heat into work or work into heat or whatever may be. Just nowhere you talked about what are the dimensions involved in a given subject or a given application. Dimensions means what is the length you need to provide, what is the thickness you need to provide to get a required amount of heat transfer. These kind of questions we didn't talk in a subject like thermodynamics. So please be careful. So now a subject like a heat transfer, where you will see a very, very important thing to design a given surface using a calculation of Q. What is the amount of heat transfer area? Like suppose a simple application, I think everybody is sitting in front of mobile or a laptop, whatever maybe. Whenever you are browsing for some period of time or using for some period of time, you know very clearly from one side of your laptop or mobile, you will see a lot of heat coming out. So in hand, to make your laptops or mobiles function properly for a long period of time, you need to improve the heat transfer from that given material. Otherwise, what will happen? These materials will be melted off over a period of time. So to overcome this, what people do or what engineers do is in hand they calculate the value of heat transfers from those surfaces. Based on those heat transfer calculation, they'll provide the required heat transfer area. You should provide appropriate value of heat transfer areas for a given surface. Otherwise, it will not function the task whatever you are given for the given surface. So these are very basic example that you can see all of you means because everybody is sitting in front of laptops or mobiles. Is it right? Everybody understood? So that means to calculate heat transfer area is our main goal in this subject club heat transfer. So we need to calculate what is the value of area of heat transfer. Area of heat transfer. Whereas in thermodynamics, in a subject like thermodynamics, we didn't talk about this kind of term. In a subject like thermodynamics, we didn't talk about a term called area of heat transfer. So our interest was in thermodynamics just to play with energy conversion. Like we want to convert one form of energy into another form. What that will do for a given... Hello?
Sir, one small doubt, sir.
Yes.
Even in heat transfer also we convert one form of energy to another, no sir?
No, not really. Mostly we play with a single term called heat transfer. We don't want, our interest is not to convert one form of energy into another form. That means we don't play with engines, we don't play with power plants here, right? We take purely one component of a power plant. Say you take a turbine blade and see how the heat transfer is happening from that single blade. You take a heat exchanger which is sitting in your power plant, take one component out which is called as heat exchanger, suppose say. In that heat exchanger, from one place to another place or one fluid to another fluid, how much heat you are going to transfer over a period of time. Clear? Understood? So please try to make a line between thermodynamics and heat transfer. That's what my interest here. In thermodynamics, we take a cumulative effect of all the components. But in a subject like heat transfer, we deal only each and every component separately, and try to design a given surface. Try to design a given surface to do a heat transfer, whatever you are desiring. Is it clear?
Yes, sir. Okay, sir. Thank you, sir.
Yeah. Welcome. So that's what our goal in a subject like heat transfer. So please make a difference. In thermodynamics, nowhere you might have learned a term called area of heat transfer. Nowhere you have seen. Because our interest in thermodynamics was not designing a surfaces or designing different kinds of surfaces. Our interest in thermodynamics was to play with how to convert one form of energy into another form. That means maybe work into heat into kinetic energy into potential energy into thermal energy. So these conversions we have done on different kinds of applications. Whereas in a subject like heat transfer, our interest is to design a given surface. Anything whatever you learned in thermodynamics can be designed using a subject like heat transfer. So that's why, broadly speaking, we use a term called area of heat transfer. So here our interest is how to design a given surface. Is it clear? Understood? So this will be calculated by calculating in hand the value of Q. Not in terms of joules or joule per kg what you have seen in thermodynamics, but in terms of joule per seconds. So we should know the value of Q. In terms of joule per second, because per second how much heat is coming out you should know. Then only you can design a given surface. It's not like per kg or joules. So you will see very commonly a term called joule per second or watts. Joule per second is also called watts, right? That's what you might have learned in your physics. Joule per second or watts. So these are the typical units you will see in the entire subject like heat transfer. which is very, very different from your thermodynamics. In thermodynamics, mostly you will see joules or joule per kg. In thermodynamics, mostly you will see joules or joule per kg. Whereas in subject like heat transfer, you will see mostly joule per second or watts, because our interest is area of heat transfer. So to calculate area for a given surface, you need joule per second. What is the amount of heat going in or coming out per second, so that you'll come to know for a period of, suppose say some 10 hours, 20 hours, how many joules has left from the surface. Based on that, you can design a given surface. So that's the first thing that you want to address in a subject like heat transfer. The second thing you want to address in this subject is mechanism of heat transfer. The second thing that you want to address in this subject is are mechanisms of heat transfer. What are the mechanisms involved? Mechanisms of heat transfer. In thermodynamics, we didn't talk about this kind of mechanisms. Please be careful. In thermodynamics, we simply took a value of Q and did a conversion to work or whatever may be, internal energy or whatever may be. We didn't bother about is there any mechanism of Q? But in a subject like heat transfer, you will see different kinds of mechanisms involved in transferring of Q. So let me include those mechanisms also. Number one mechanism is conduction. The mechanism of heat transfer is conduction. Number two, it is convection. Number three, the third type of mechanism is radiation. Number one is conduction, convection, radiation. So these are the very, very important mechanisms of heat transfer, which you will see in the later sessions of heat transfer subject, which were not addressed in a subject like thermodynamics. So which we will see more in depth in a subject like heat transfer. So any questions? Any questions here? Anyone, any doubt? Everybody clear? Is my voice clear, or anything that you want to give a suggestion?
It's clear, sir.
Yes. Remaining people, everybody clear? If you have any queries at any point of time, you can unmute your call and you can talk, no problem. Nothing to worry. You can stop at any time, you can ask questions. So these are the broad things that you want to address in a subject like heat transfer. Number one is a designing purpose, how to design a given surface. Any application you take, this is what is required. You take any small application from your kitchen to a flying aircraft engine, a rocket, a missile, or whatever may be. All these things, very small to bigger applications, you will see a subject like heat transfer. Without this subject, these components cannot be designed. Are you guys clear, everybody? A small burner sitting in your kitchen, right? You do cooking, right? Everybody in your home do cooking, right? For cooking purpose, you will use burners, right? Which is sitting at the center of your stove. So that burner also designed based on these calculations only. Okay, clear? So that's what my intention here is. This is not a simple subject where you will see for a small number of applications, not like that. This subject has to be applied, will be applied. A very small application sitting from your kitchen to flying aircraft engines, rocket, missiles, or whatever. So that's how you need to see this subject. Okay, and very important, this subject is not only useful for mechanical people, this is highly useful for chemical people, aerospace people, right? Material science people, most of the engineering people, they use a heat transfer subject. Even electrical people also, they want to design a heat transformer, suppose say heat transformer, electrical transformer. So based on the calculations of amount of heat generation, they need to design a given surface for a transformer. So all these things are included in a subject like heat transfer. That's why this is a common subject for most of the engineering students. Right, clear? So now at this point of time, let us see mechanisms of heat transfer first. Let us try to learn how a conduction happens, how a convection happens, how a radiation happens. Then let us see some governing laws for each mechanism of heat transfer. Then we will jump into each chapter of conduction, convection, and radiation. Then in those chapters, we will address a very important term called how to design a given surface. Right? Clear, everybody? Understood? So let us go to the mechanisms of heat transfer now. Let us go to the mechanisms of heat transfer now. Mechanisms of heat transfer. Mechanisms. In that, the first one is conduction. In that, the first one is conduction. Let us see how conduction happens. In that, the first one is conduction happens. In that, the first one is conduction. Let us see how conduction happens or conductive heat transfer happens. Right, clear? So to understand this, I'll not define anything first. I'll try to take some physical example which happens in reality. From there, we'll define how conduction happens and all. Let us take a solid rod or solid body. I'll take a solid rod, suppose. So you have a solid bar or rod or whatever it may be. So something like this. Right, clear? Say I'll choose two locations mainly. Say this is what is x equal to 0. This is what is x equal to L. And let me give you some boundary conditions in terms of temperatures for this surface. Suppose this is T1, T2, T1 and T2. And let us assume your T1 is greater than T2. Let us assume your T1 is greater than T2. Right? And you know from our thermodynamics knowledge, for if you keep or if you maintain a value of delta T between two locations, heat transfer happens. That's a basic fundamental for the entire subject. Is it correct, everybody? If you maintain a value of delta T, between two locations, there will be a heat transfer from one place to another place. So that's the entire concept in the entire part of heat transfer subject. So here also we are trying to do the same thing. We are maintaining two surfaces at different temperatures, say T1 and T2. In that, I'll choose such a way that x equal to 0 surface is a T1 which is greater than x equal to L. T1 which is greater than x equal to L surface. So which means that heat is flowing from x equal to 0 to x equal to L. Heat is flowing from x equal to 0 to x equal to L. Is it clear? So I am defining the type of material here. This is solid material, right? You will be having three phases: solids, liquids, and gases. Let me choose first purely solids. Let us see what happens in the case of solids. Then we'll jump into liquids and let us see gases later. So if it is a solid, how the arrangement of molecules? So if I take a cross section of this, that means taking a knife and cut parallel to your front surface. Whatever you are seeing in the front side of the board, you just cut the bar parallel to that. What you will observe here is after cutting, I'm just taking the cross section area out. This is how it looks, right? Everybody clear? This is what is x equal to 0. This is what is x equal to L. The same T1 and T2. I'm just taking one plane out. By cutting parallel to your area, which you are seeing in the front side. So now if you see the arrangement of molecules inside this solid body, a solid rod or bar, whatever it may be, the molecules are tightly packed. Because of the nature of the phase. The molecules are tightly packed. So that means there won't be much gap between the molecules. so that the molecules are completely arrested to move. The molecules are completely arrested to move. So suppose say what is physically happening here is you are heating the left surface to maintain a T1. You are heating the left surface which is sitting at x equal to 0 to maintain the surface at T1. Whereas at the other end x equal to L which is maintained at a lower temperature which is T2. So now that means basically what you are doing from your thermodynamics perspective is you are basically pumping in the energy in the form of heat. Pumping in the energy in the form of heat. So when you are pumped energy in the form of heat, the first layer of molecules, the first layer of the molecule, say these are first layer, say layer 1, has got the energy. Is it right? The first layer of the molecules which are close to the x equal to 0 surface has got enough energy, but when they got the energy, what they'll try to do, they want to move, but being closely packed, they're completely arrested to move. They're completely arrested to move. So therefore they cannot move now. They cannot move now. So what they'll do with that energy, what it got means they try to vibrate locally. If you take a single molecule out, they try to vibrate local. They try to vibrate local. That means molecules start to vibrate local. Molecules start to vibrate local. Is it fine, clear? So now when the first layer of molecules which is close to x equal to 0 surface try to vibrate locally, these vibrations will be transferred to the next layers. These vibrations will be transferred to the next layers with respect to time. Is it right, clear? So slowly what will happen, so these molecules try to vibrate locally at every layer with time. So slowly what happens, whatever the energy you have pumped in at x equal to 0 is getting transferred from x equal to 0 to x equal to L in the form of vibration of molecules. In the form of vibration of molecules. So technically speaking, this is what is called as phonons. Technically speaking, this is what is called as phonons. That means vibration of molecules, if it is occurring and you are seeing a transport of energy from one surface to another surface or one location to another location, then that is what is called as technically a type of mechanism is called as phonons. Type of mechanism is called as phonons. Is it clear? Everybody understood? Everybody? So this is happening only because of arresting the molecules and saying that not to move. Arresting the molecules and saying that not to move. If you are allowing the molecules to move, it just moves and transfers the energy. But in the case of solids, what you have learned in our school level physics or chemistry means molecules are tightly packed. They are not allowed to move. That's the difference between solids, liquids and gases. The first difference you will see between solids and liquids means the molecules are very tightly packed. They cannot move that easily what you will see in liquids and gases. Because of that nature, the molecules are completely arrested to move. So therefore, which results in local vibration of molecules at any layer. So which leads to transport of energy from one surface to another surface. So this is what is technically called as phonons. So this happens in any solid. At a molecular level when you are maintaining a temperature difference. This happens in any solid at a molecular level when you are maintaining a temperature difference. So let me include one more statement here. Say solids, if I am interested completely into metals, suppose that. Whatever I have spoken here up to now, they are completely valid for any solid. Let me take a particular solid called metals. Metals are the solids, right? We know that. Metals. Let me take a particular solid called metals. So what's the difference between metals and non-metals at the molecular level means you will be having availability of free electrons.
Free electrons.
Yes, correct. Availability of free electrons. Is it right, everybody? So now that's the extra advantage that you will be getting. That's the extra advantage you will be getting compared to non-metals. In non-metals, we don't have any free electrons. Only the effect is, only the transport of energy is because of vibration of molecules. Whereas in the case of metals, apart from carrying because of vibrations, these free electrons also acts as energy carriers. Also acts as energy carriers because they got the energy, they are free to move. Electrons are free to move, they are not getting obstructed like your molecules. So these electrons get the energy from the surface which are at higher temperatures. They are free to move. They'll move from one location to another location and transport the energy apart from your vibrations. So in the case of metals, you will see both the phenomena. One is phonons as well as motion of free electrons. In the case of non-metals, you will see only one phenomena, which is phonons. Let me include here. So solids, the transport of energy, if you see, particularly transport of heat, right? Energy in the form of heat. You will see based on two kinds of solids. One is metals, the other one is non-metals. In the case of metals, we'll be having two things. One is because of phonons and because of motion of free electrons. Right? In the second case, non-metals, which we have discussed, the first non-metals, you will see only because of phonons. Only because of phonons. Everybody clear? How a transport of energy happens? How a transport of energy in the form of heat happens in the case of metals and non-metals? Everybody clear? Is the things visible clearly?
Yes, sir. Clear,
Yeah.
sir. What is
Thank you.
phonons exactly, sir?
Phonons means the simple thing is vibration of molecules. Transport of energy because of vibration of molecules. That's the mechanism of conduction, which is happening locally. You will see that statement later, but I am not defining the conduction now. That's why I am talking in terms of vibration of molecules. So exactly what does phonons represents means vibration of molecules locally. Vibration of molecules locally. Remaining people, is it clear? Any doubts?
No doubt, sir.
Thank you. Let me go to the next slide. So this what is the thing coming from solids. So if I choose a different phase, something like liquid, suppose, let us see what will happen. If I choose a different phase like liquids and gases, let us see what will happen here. Say, let me go to liquids first. Right. So to talk about this kind of phase, let me choose, suppose, two surfaces. Let me choose, suppose, two surfaces, and in between these two surfaces you are having some liquid which is at rest. You have some liquid which is at rest, say some water, some mercury, some oil, some petrol, some kerosene, whatever may be, which is at rest. So please be careful, I'm using a word called rest. Okay, and these two plates are maintained at different temperatures. So this is a T1, this is T2. And again the same scenario I'll take, which is T1 greater than T2. This is T1 greater than T2. Right? So what will happen now? So the top plate is at a higher temperature. Again the same situation. The molecules close to the top surface gets the energy. Right? Now they are allowed to move, not like your solids. Now they are allowed to move. So when they are allowed to move, what they will do, they will go and hit the next molecule, which were at rest earlier, in the earlier case, and transport the energy which they got in the previous time, and transport the energy during that collision, which they got in the previous time. So like this series of collision happens from top to bottom. So slowly these collisions will increase with time, and the energy what they got in the top surface at the previous time will be transferred to the bottom surface in the later time. Is it clear, everybody? So this is the difference between solids and liquids. In solids, they are completely tightly packed. That means they are not allowed to move. The molecules are not allowed to move. Whereas in the case of liquids, they are little far compared to solids. So therefore, they have an advantage of moving from one location to another location. But it's not like completely from top to bottom. Before going from top to bottom, they have to undergo a lot of collisions during which they need to transport the energy. During that collision, they need to transport the energy what they got in the earlier time. So due to which the transport of energy happens from top to bottom. From top to bottom. So therefore, the kind of physics that you will see is little simple compared to solids. So here the energy transport. Here the energy transport is due to collisions. So please be careful in the subject like heat transfer. There is nothing like different energies. Energy means heat. That's it. Heat transport is due to collisions. Collision between molecules. Due to collision between molecules. Collision between molecules. Is it right, clear? Everybody understood? So if I go for the next phase, which is say gases, I think now you can extrapolate the things from what you have learned from liquids. Now these are very far. In this case, the molecules are very far. I don't want to draw the same figure. Molecules are very far. Very far. Since they are very far, the molecule, each molecule has to travel a lot of distance, before undergoing for a collision or transport of energy. Before undergoing for a next collision or transport of energy. So therefore, what you can say very clearly here, compared to liquids and gases, the transport of energy due to collisions are less. Is it right? The transport of energy due to collisions are less when you take gases compared to liquids. So here also the same statement will be included. That means transport of energy is due to collision between molecules, but the transport value, whatever you are going to transport, the transport value is less or lesser than liquids. Lesser than liquids. Is it right, clear? Everybody understood? In all the situations you will see, the initial state of the system may be solid, liquids or gases, whatever may be, the initial state of the system has to be at rest. The molecules, whatever are taken initially, has to be at rest before transport of energy. So that's why this is what is technically called as conduction or conductive heat transfer. So how you define conduction now? How you define a conduction now? By including all the three phases. You need a heat transfer. Suppose if you are doing a heat transfer, with no bulk motion. Is it right, everybody? No bulk motion. No bulk motion means no velocity in the problem. Heat transfer with no bulk motion. That's the meaning of rest. Heat transfer with no bulk motion. But with phonons and motion of free electrons, in solids, because of collision of molecules in liquids and gases. So if you see this kind of scenario in a problem where you want to transport of energy, that is what is called as conductive heat transfer. Everybody clear? Any questions now? Anybody any doubt? Anything that you want to discuss about conduction? How a conduction happens means, number one, a very important condition for conduction means no bulk motion. The molecules has to be at rest. Number two, you should think about the phases, the solids, liquids or gases, which you want to talk about. If you take solids, it has to happen either because of phonons or phonons plus motion of free electrons based on metals or non-metals. That's a broad view of solids. A second thing, if you're talking about liquids, it must be because of collision of molecules, and similarly gases also. In all these three phases, important condition to satisfy is no bulk motion. Important condition to be satisfied is no bulk motion. Is it clear? So now where the conduction happens very easily, that's what my next question. What do you answer? Where the conduction happens very easily. What is the answer for that?
In solid surface only.
Very good. Because the molecules are very close, it's easy for it to transport energy from one end to another end. Is it right? That's very clear, right? From the figure itself, we can tell. Whereas in liquids and gases, it's very tough because a molecule has to travel a lot of distance. During the travel, it may lose some energy. It may lose some energy because of friction, because of viscosity, or whatever may be the reasons. But in the phase like solids, it's very easy for transport of energy. In that solids also, it's very easy in the case of metals. Is it right? In solids also, if you take metals, the easiness in doing conduction is very comfortable because you have an extra effect, which is motion of free electrons, which is not there in the case of non-metals, So that's why conduction is highly dominated in the case of solids compared to liquids and gases. So that's why most of your real life examples, you will see conduction mostly in solids, not in liquids and gases. It doesn't mean that conduction is not happening in liquids and gases. It happens. The values are very, very minimal. So generally speaking, what we do in a subject like heat transfer subject under B level, we take the examples in the class also where conduction happens in solids only. We don't talk much on liquids and gases. So what we can tell here is conduction in solids. I'll use an extra advantage which is much greater than conduction in liquids is greater than conduction in gases. Is it right? Clear? Everybody understood the statement? Conduction in solids, because of having multiple extra effects compared to liquids and gases, I can take an advantage of giving much greater than compared to liquids and gases. So this is what happens in reality. And I'll use it one more statement here. If you take solids, I have one more effect here. Conduction in metals, that also can be included, is greater than conduction in non-metals. That is also included, right? Conduction in metals is greater than conduction in non-metals. That also can be included. So broadly speaking, so if you want to do a conductive heat transfer, pick a material which is metal. Is it right? For a kind of application, what you see in reality, if you want to do a conductive heat transfer, pick a material which is mainly metal. If metal is not available, go for a non-metal. Any questions up to now? Anyone, any doubt that you want to ask?
Nothing.
Clear? Remaining people clear? Right? So with this understanding, let us go for governing law for conduction. Governing law for conduction. Governing law for conduction. Governing law for conduction. my pace of teaching is fine, right? Am I going slow or fast? Or is it fine? Everybody comfortable? If anybody is not comfortable, please let me know. We can
It's
unmute.
comfortable one.
Remaining people, if it is not comfortable, please let me know by unmuting your call. Please tell me if I am going fast, suppose say. Please tell me if I am going slow also. Everything is taken care, no problem. So governing law for conduction. Governing law for conduction. So which is technically called as Fourier's law of heat conduction. Fourier's law of heat conduction. So HC means heat conduction. Fourier's law of heat conduction. So please be careful. This heat transfer subject is completely developed or evolved by means of mathematicians like your fluid mechanics. All these subjects, both fluid mechanics and your heat transfer, both developed by mathematicians, not like engineers. But we engineers are using this concept for our real life applications. For real life application, not like your design, strength of materials, thermodynamics, where you will not see much math in a given class. Is it right? There you will see only the concepts related to that, and we'll do a very little amount of math and get the solutions. Whereas in a subject like fluid mechanics and heat transfer, you need a lot of mathematics. Like at least first order of maths, like you should know how to solve a differential equation. You should know how to write partial differential equations, integrations, limits. So these kind of things you should be good at. Means you should be good so that you can learn these subjects very easily. Otherwise, you will feel like some kind of discomfort when you're learning these subjects. So please make your mathematics a little bit strong whenever you're reading a subject like heat transfer and fluid mechanics. But because they're completely involved in math. Why? Because they are developed by mathematicians. These subjects were developed by mathematicians. So let us go for a first governing law, which is called as governing law for conduction. So to understand this law, let me take the same figure what I have drawn already. That is the same cross section of the bar. The same cross section of the bar. Okay. So this is what is our x direction. And you are maintaining a value of delta T by picking a values like T1 and T2. And you want to do a heat transfer Q due to conduction. So why I am telling conduction means there is no bulk motion here, bulk motion of molecules. So it's conduction purely, right? So now suppose say I have a small region in this direction, x direction. Say this is what is our dx from say a location t, which is at some x, to something like t at x plus dx. So that this is maintained at delta T or dt. The temperature difference between two surfaces in that strip is maintained as dt or delta T, so that you can comfortably transfer heat. That's a main statement you have to satisfy to do a heat transfer. What is that means? You need a delta T to talk about heat transfer. You need a delta T to transfer a value of heat or heat transfer. Is it right? So now what you can tell from here, from our common sense, from our physical intuition, what you can tell here is the amount of heat that you are transferring here, a Q value due to conduction, is directly proportional to your dt. Is it right? More the value of dt you are having, more the heat you can pump in. Less the value of dt you are having, less the value you pump in. That's it. Is it right, everybody? If you have more temperature difference, it's like similar to your suppose you are sitting in Chennai, suppose you have a very high temperature during summer outside. In the room you will be having lesser temperature, suppose because of running of AC or what I'm doing. So whenever the air sees a difference in temperature, you will see a heat transfer from outside to inside your room. If you are having a delta T more, suppose during afternoon or mid of 11 or 12 o'clock in the morning, you will see more heat transfers. More the delta T you will see, more the heat transfer you will find due to conduction. The second thing which is very clear from here is a dx value. If your distance between two surfaces, if it is large, suppose say, if the distance between two surfaces are large, then it is very tough to transfer heat, right? If the surfaces are very close, then you can transfer heat very comfortably or very easily. Let me repeat once again. if the distances between two surfaces, whatever you are choosing, say x equal to 0 or x equal to L, if those distances are very small, it will be easy for you to transfer heat. It will be easy for you to transfer heat. Suppose the same two surfaces are very far, then it will be tough for us to transfer heat. So that means it is inversely proportional to dx. It is inversely proportional to dx. Everybody agrees with this? So now one more thing, you are transferring heat into some area, right? Area which is sitting in the direction of x. Area which is sitting in the direction of x. So please be careful whenever you are talking heat, you want to transfer heat into a given surface area. Into a area. It is entering perpendicular to a given area. It is entering perpendicular to a given area. Just for your understanding purpose, let me extract the figure, extrapolate the figure like this. So this area you will see in the z direction. So this is the area into which you are transferring heat. Is it correct? That is the area into which you are pumping in the energy. Say if your area is more, if the area which is available to do heat transfer is more, you can pump in more heat. If the area is very small, you can pump very small amount of heat. Is it right, everybody? So again, it is proportional to area. More the area, more the heat you can pump in. Less the area, less the heat you can pump in. So therefore, it's proportional to area. It's proportional to area. Is it correct, everybody? So if you combine all these common sense statements, what you can get is Q proportional to A dt by dx. Is it correct, everybody? Q proportional to A dt by dx. Any doubt in writing like this? If the value of dt is more, I can transfer more heat. That's a statement coming from your thermodynamics. If the value of dx is more, it's very tough for me to transfer heat. If the dx is very small, it will be easy for us to transfer heat. Similarly, area. If area is more, I can pump in more heat because available area is more. If the same available area is less, I cannot transfer much heat. Right? So combining all these three statements, what I can write is Q is proportional to A dt by dx. So now let us choose two materials of the bar. Let us choose two materials of the bar. Say one is an iron rod. Suppose say the bar is made of iron. The second one is suppose some plastic material or wood. Plastic materials or wood, whatever. I'm smartly choosing two materials so that one is a metal, the other one is a non-metal. This is a non-metal. Correct, everybody? So now let us keep the conditions same between two materials. Say I'll pick the same delta T, I'll pick the same value of length of the bar, I'll give the same area of heat transfer. Is it clear, everybody? I'm taking two materials and two conditions of the problem such that in both the problems I'll keep all the conditions same. All the conditions means the A, the dt, dx. All the three conditions same between two materials. We know very clearly the value of Q what you get will be different because of our previous understanding. Because of our previous understanding, just now we have understood how a conduction happens in a solid, especially metals and non-metals. We know very clearly from our earlier discussion, definitely the value of Q should come out as different. Even though you keep a value same, a dt value same, a dx value same. Because something is depending on the type of material. That means you need to include some property which depends on type of material. That is what is technically called as thermal conductivity. So therefore, I'll remove this proportionality. I'll use Q equal to minus Ka dt by dx. minus Ka dt by dx. And why the minus came here means you are moving in the negative temperature. That means you are moving in a direction where you are seeing temperature drop, right? You are moving from T1 to T2. When you are moving from T1 to T, you will see always temperature is decreasing. Temperature is decreasing. When you evaluate the value of delta T or dt, you will see a negative value. But Q is moving in the positive x direction. But Q is moving in the positive x direction. So to make a sense for Q, that means when you are moving in positive direction, you should get the value of Q positive. When you are moving in the negative x direction, you should get the value of Q negative. So to make that sense, because of having temperature gradient negative, you should get the value of Q positive means I need to have one more minus sitting in front of the term. So that's why you are adding one more negative sign. Whereas the constant what you have introduced now, is K, which is technically called as thermal conductivity. This is very, very important. Thermal conductivity, which is property of the material. Which is property of the material. Is it clear, everybody? Thermal conductivity, property of the material. So let us see what's the unit of thermal conductivity. That's also a very, very important question which they are asking in the exam very regularly. What's the unit of thermal conductivity? So I told you in a subject like heat transfer, the units of Q is joule per second or watts, right? Joule per second or watts. So watts, suppose say, divided by A is meter square, and dt it's a difference in temperature. You can pick in Kelvin or degree centigrade, doesn't matter because the value is same. It's Kelvin, suppose say, K, or degree centigrade also doesn't matter, divided by dx, the value of distance is meter. So which comes out as watt per meter Kelvin. So very important, please be careful. Watt per meter Kelvin is the unit of thermal conductivity. So some people they use watt per meter degree centigrade also. Don't confuse, because you are seeing a term called difference in temperature. When you're talking difference, don't bother about whether you're using Kelvin or degree centigrade. The answer will come out as same. Okay, since you are using dt in this particular statement, so therefore degree centigrade Kelvin doesn't make any difference. So any questions here up to now? So this is what is called as governing law, and this law is derived from just observation. There is no proof for this. Please be careful. Those kind of statements or laws are called as governing laws. There is no proof for those kind of things. These are completely observed from experiments. These kind of laws, like whatever you learned in your thermodynamics, also first law of thermodynamics, second law of thermodynamics, they doesn't have any proofs. They are governing laws. They are just simply observed from experiments. Like in your engineering mechanics, you have Newton's laws, right? Newton's first law, second law, third law. They also doesn't have any proofs. They are simply governing laws because they're completely taken from physical observation. Or experiments in the lab. They don't have any proof at all. So don't expect any proof for these kind of statements. This is what is called as Fourier's law of heat conduction. So very important takeaway from this statement is there is a property called thermal conductivity, which is depending on the material, type of material you have chosen for the conduction to take place. That's very, very important. K. So units of K is watt per meter Kelvin. So any questions? Anybody, any doubt? Anywhere, any doubt? Anybody? Okay. If it is fine, we'll take that advantage of Q conduction is highly dominated in solids compared to your gases, compared to your liquids also. So again, keeping all the conditions same, why why the Q's different will come means because of K, right? Because the K of your solids, I'll use some different color. K of your solids must be very, very high compared to your liquids, compared to your gases. So in these solids also again you can expand. Again you can expand. What is that means? K of metals, very important statement, is greater than K for non-metals is greater than K of liquids is greater than K for gases. K for gases. Any doubts? The statement is clear, right? From your understanding of mechanism of conductive heat transfer. From the understanding of mechanism of conductive heat transfer, we are writing a statement like this, which is K of metals is greater than K of non-metals, is greater than K of liquids, is greater than K of gases. Any questions? So just to get a broad feel for K, I'll give a plot. Say this, what is the x-axis is, sorry, y-axis is some material, and the x-axis is thermal conductivity, K, which is written in watt per say, meter Kelvin. And let me divide the x-axis into some ranges. So it is 0.01, suppose say 0.01, followed by say 0.1, followed by some 10, some 100. Just to get a feel for numbers, how the K values looks in reality. So very, very small values of K, very, very small values of K are falling in this region, very close to 0, right? So these are technically called as insulators. A poor heat conductors. Is it right? Poor heat conductors are insulators. These are insulators which are poor heat conductors. For some applications we need this. For some applications we need. For some application we need poor heat conductors. Like practical examples are your refrigerations, air conditioning systems. All these surfaces they'll having some kind of coating. Like if you see the refrigerator, they'll give some coating, right, for the outer surface. The purpose of that coating is those coatings will act as insulators so that heat will not flow from your surrounding air into the refrigerator. Why? Because whenever you run a refrigerator for a period of time, you will see there is a large temperature drop in your refrigerator compared to your surroundings. That's the purpose of refrigerator. So whenever you see this kind of drop, one second. Whenever you see this kind of temperature drop, there will be a heat transfer. From the surrounding air into your refrigerator where you kept all your fruits and vegetables or milk or curd, whatever. So if that happens means with the time there is a lot of power waste. Which is not good, right? You are supposed to pay a lot of power bill. So to make this or to arrest this kind of things, what we do as an engineer, we provide some kind of material coating on the outer surface of your refrigerator air conditioning system, which will not allow heat to go into your refrigerator, and which will reduce your electrical bill. which will reduce your electrical bill. The same kind of application you will see in the case of air conditioning systems also. Air conditioning systems also. So those are called as insulators, poor heat conduction. And similarly, you can expect the same kind of situations in your power plants. Like if you take a boiler, where the purpose of boiler is to burn a lot of fuel and liberate the energy from that fuel, and then give to the surrounding fluid, which is water, to convert it to steam. Is it right? That's what the purpose of boilers. So during this addition of heat from your fuel to your water, you should not lose the heat to the surroundings. So what they do in hand smartly is they'll provide the boiler material with bricks. Why? Because bricks are poor heat conductors. So they will not allow the heat from your boiler in chamber to the surrounding air. A similar kind of things you will observe in your gas power plants, all the engines, everywhere, where you need insulators during your combustion. Why? Because you want to efficiently add heat, whatever has liberated during your combustion, to the surrounding air, so that you can use that energy for rotating your turbine efficiently. Is it clear? So those are the places where you will see varieties of insulators. What the purpose of this means? To reduce the heat transfer. Next range, what you are observing here is very close to 0.1. Here the material what you will come out are gases. These are range for gases, very least. Next to your insulators, the materials what you observe will be gases. Then followed by gases around a range of single digit numbers, which you will get are liquids. I'm just giving the sense of numbers. No need to remember the exact values. Don't bother about the exact values. Exact values may be a little different, but at least get a feel for range. In what range, what type of materials are following. Then followed by the next one. I'll not go directly to the next one. I'll pick the last one. What do you expect the last one? Come on. What do you expect the last one? Anybody? Any guess?
Solid one.
Solids also you have two, right? In that two, what do you expect? Solids, we have two types of solids. What type of solid you will pick for the higher K?
That is metal.
Metals, very good. So I'll choose for higher range of K, metals. Very good. Higher range of K, I'll choose metals. So these are close to 200s, 300s or more. Up to 400. Then in between these two, you'll be having one more, which is non-metal. Close to 100. Non-metal. So in between metals and non-metals, what do you expect? Between metals and non-metals, what do you expect from your chemistry or physics, whatever you have learned in your school level? Mixture of metals and non-metals, right? You can take some percentage of non-metal, you can take some percent of metals, you can mix, and you'll get some equivalent some type of material which we technically called as what are those called as? If you mix
Alloy.
some portion of non-metal,
Alloy metal.
alloy, very good. Alloys are semiconductors, right? In this range, whatever you get are alloys, are semiconductors. Alloys are semiconductors. So these are the broad ranges for different kinds of materials. So that's why if you want to play with conduction, we always prefer metals. That's why you see most of the metals in your combustion engines, aircraft engines, everywhere. Wherever you see heat transfers, you will see mostly metals, not non-metals. Metals followed by insulators. Metals or insulators. We don't see any of these two like non-metals, liquids, gases. Very rarely we see for some particular applications, not in terms of normal real applications. Normal real applications. Some applications where you want to work with say very high temperatures, where some properties has to be taken care apart from K. At those places, you will see different kinds of alloys and non-metals, but not regularly as what you see metals. As what you see metals. So generally speaking, the value of K is very high for silver. Very close to 400. Don't try to remember the exact values. Exact values nobody will ask you. Just know the range where the K for a metal, especially silver, lies. And then followed by copper. Followed by copper. This is again close to 350. 380, 360, something close to that. Then followed by the remaining metals. Then followed by remaining metals. Is it clear? Everybody understood? So, what's our interest in learning this means? From now onwards, we mainly concentrate on these kind of materials. We mainly concentrate on these kind of materials. No, they will not allow any data handbook. They'll give you the required values, whatever you want in the question itself. Fabian Marshall. Hello? Fabian Marshall. You can unmute and you can talk, no problem. Am I audible? Fabian Marshall? What happened to him? Why you are just sending message? You cannot talk, huh? You can. Oh, I have unmuted the calls, huh?
No, sir, you haven't unmuted any calls, sir.
Then why he is not talking? He is simply sending message. He's asked me question, will they allow the usage of that data handbook in the exam? The answer is no. But why he is not talking? I don't know why. What happened, Marshall? Am I audible?
Sir, one small doubt
Okay.
is, sir, one doubt, sir.
Hmm.
Alloys are combination of metals, one, metals and non-metals is another. But since it's a combination of metals, it means heat conduction should be even more, no, sir?
No, that should fall in between, right? You are not taking a pure metal, you are not taking a pure non-metal. You are taking some quantities from non-metals, some quantities from metals, and you are doing a mixture.
Average.
So always it should lie in between, right?
What about mixture of metals, sir?
That's a different story again. There is something like equal and thermal conductivity which we need to calculate again. So suppose if you take silver and copper, a mixture, the value will be close to silver or little higher than silver.
Yes, sir.
It's basically speaking, you are not when you are mixing. No, you are not in your interest is not on K. Your interest is to take the extra properties of copper compared to silver. That's why that's the purpose of mixing. Say some properties are weak with silver, some properties are very good with copper. Apart from K, suppose. So you want to include those properties also into silver apart from K.
Got it, sir.
Understood what I am telling you?
Yes, sir. Got it, sir.
But the value of K will not go more than silver.
Okay, sir.
Is it clear?
Very clear, sir.
Yeah. So that's the advantage of going for alloys. So this is a broad view of range of K for different materials. So please have a look at these ranges. Don't bother about the magnitudes. Just see the ranges so that in real application, whenever you go for say working in some industry or some place where you are going to work with some heat transfer problems, if they ask you to choose a particular material for a given application, you need to be very clear with what kind of material you have to choose for a kind of application they are given with. So you should not pick a material. Suppose you want to improve heat transfer, means don't pick a material which is insulator. Don't pick a material which is non-metal. So prefer a material which is metal, and you have to be very optimistic also. Like if you go for picking a silver because of higher conductivity, you are investing a lot of money. So there also you have to be very clear. So if I choose a silver, I need to spend a lot of money, whether that is useful in a kind of application or not. If not, go for the next least, like a copper, aluminum, iron. So these kind of things has to be taken depending on the amount of investment of money they are doing. So these things will be answered when you go for a subject like operational research and all, right? Clear? So that's what you have learned from this topic. Let me repeat once again. So if you go to the previous slide, so we have started with mechanism of heat transfer, which is conduction, the first one. So there, what the conclusion we got is this conduction will be talked only when there is no bulk motion. Only when there is no bulk motion. And once again, in some textbooks, they call the same conduction as diffusion also. Don't confuse. Some advanced level textbooks, they use a term called diffusion instead of conduction. Diffusion instead of conduction. That's again clear, right? Diffusion means what? Spreading. You want to spread the information. What's the information here? The information is information of temperature. It's just spreading from one location to another location without any bulk motion. That is what is technically called as diffusion. So conduction, in some textbooks they call the same type of heat transfer as diffusion. Same type of heat transfer as diffusion. So the governing law is Fourier's law of heat conduction, which is minus Ka dt by dx. Right, clear? Minus Ka dt by dx. And the units are watt per meter Kelvin. And since the conduction is dominated in solids, you can straight away take how the K changes between different kinds of materials, and this is a plot you are getting. And this is a plot you are getting. So sometimes instead of using a value of K, what people prefer is heat flux. What people prefer is heat flux, denoted by small q. Denoted by small q. It is very similar to your mass flux, what you have seen in fluid mechanics. Mass flux. Mass flux means mass flow rate per unit area. Is it right? Mass flow rate per unit area. And similarly, momentum flux. Momentum flux. What does that mean? Means momentum per unit area. So anything per unit area is called as flux. Anything per unit area is called as flux. Similarly, volume flow rate flux, which is volume flow rate to unit area. So any quantity you are dealing per unit area is called as flux. So here in this subject like heat transfer, we call the same kind of things as heat flux, which is heat transfer per unit area. Heat transfer per unit area. Units for this is straightforward, which is watt per meter square. Which is watt per meter square. Watt per meter square. So the equation, if you see the conduction equation for this, Q will come out as minus K dt by dx. So if you are evaluating this term in the x direction, this happens to be Qx. Flux in x direction. Flux in x direction. Because flux is a vector, right? If you are taking care of area, the flux becomes a vector. So similarly, you can write Qx, Qy, Qz in a three-dimensional form, say Qx I cap, Qy j cap, Qz k cap. So in the previous expression, when you write something like this dt by dx, our assumption was that T is varying with x. Is it right? The temperature T is varying with x. So if you want to extend this kind of equation to three-dimensional form, what you have to assume is T is a function of x, y, z. T is a function of x, y, z. And K also varies, may be varying with x also. So what you can write here, minus kx dou t by dou x. Please be careful. I'm writing partial derivative because it's function of multiple variables now. Into I cap minus ky dou t by dou y j cap minus kz dou t by dou z k cap. Is it clear? Minus kx dou t by dou x I cap minus ky dou t by dou y j cap minus kz dou t by dou z k cap. That's also fine. The same thing can be extrapolated. Instead of assuming t as a function of x only, if you take t function of multiple variables x, y, z, the same expression can be rewritten. Instead of ordinary differentiation, you have to write in partial differentiation in the corresponding direction. So this can be written as q bar, right? Q bar is a vector. Q bar equal to qx I cap plus qy j cap plus qz k cap. So which is equal to, say if k is constant, suppose say k will come out or minus k will come out, dou t by dou x I cap plus dou t by dou y j cap plus dou t by dou z k cap. Everybody agrees with this statement? I'm assuming k as a constant, it is not varying with x, y, z directions. X, Y, Z direction. That means it's called as isotropic material, right? That's what you might have learned in your strength of materials. If a property is independent of direction, those materials are called as isotropic materials. So here the property is K. Let us assume it is independent of direction Kx, Ky, Kz. They are saying minus K will be taken out, and the remaining terms can be written as dou t by dou x I cap, dou t by dou y j cap, dou t by dou z k cap. So therefore, from our vector calculus knowledge, this can be written as minus k del t. Is it right? Minus k del t. Where del means, just including the math here, little bit of math. Form of del that you have learned is dou by dou x of I cap, dou by dou y of j cap, dou by dou z of k cap. And this operator is applied on temperature. So sometimes people expect a same quantity in three-dimensional, sometimes people expect in one-dimensional. So you have to be comfortable in conversions. Please be careful. Only thing is, instead of giving t function of x, they'll give you t function of x, y, z. Just substitute in that equation, get the derivatives, and then add all the three. You will get the total heat flux vector. If they want to know the total heat flux, just take a magnitude of that. You know, right? Square root of qx square plus qy square plus qz square. I think, see, these kind of things you might have done in your mechanics itself. Force balances, fx, fy, fz, square root of fx square plus fy square. Same things, nothing new, because they are all vectors. They belong to the same kind of family. Any questions here? Anywhere, any doubt that you want to discuss? Understood conduction? So this is what is a conduction, how conduction happens. This is a mechanism of conductive heat transfer. If it is fine, let us jump into the next type of heat transfer, which is convection. Next type of heat transfer that we are interested is convection. So again, let us take some example, real life example, try to understand how it works. Then based on that, we'll define how convection happens. Let us assume a flat plate. Let us assume a flat plate which is at rest. Say there is a flat plate which is at rest. Say let us assume this plate is at a temperature of Ts, plate temperature of Ts, which is constant. I'll take a simple problem where it is a constant. This can be variable also, but I am taking a simple problem just to understand the things easily. Ts is a constant, and because of fixing, the velocity is also zero. Velocity of the plate is zero. Is it fine? And this is exposed to some fluid, and this is exposed to some fluid which is coming from left to right. Exposed to some fluid which is coming from left to right with a velocity of say u infinity meter per second. And let us assume this fluid, the free stream fluid, is having a temperature of T infinity. And you can define the mechanical properties as well as thermal properties here. One is you are interested in say viscosity mu from your fluid mechanics perspective, and density rho. And coming to thermal knowledge, thermal properties, we are interested here is specific heat C, right? Specific heat C, and then K. Just now we have seen thermal conductivity K for a fluid, maybe liquid or maybe gas. So these are the properties you are interested now. These are the properties you are interested. From now onwards, this is the problem you might have seen in fluid mechanics, the same problem with these kind of numbers. Whereas now we are adding extra 3 for the existing fluid mechanics problem. I guess clear? I kept in 2 boxes. One box corresponds to fluid mechanics problem. The other box corresponds to heat transfer problem. And you are combining both, and you are studying in a subject like especially convection. Clear? Understood? Then let us talk about first fluid mechanics problem. Then we will jump into heat transfer problem. Don't bother about the temperature effects. Let us see what happens to these velocities. Now, this plate is at rest. The fluid molecules which are close to the plate, see this is what is a x direction. Let me give you the coordinate system for understanding purpose. Say I am picking a Cartesian coordinate system. This is what is x direction. This is what is y direction. Right? Clear? Fine. So I'll choose the first layer of the fluid molecules. First layer. A layer of molecules which are sitting close to the plate. That means at y equal to 0. This is at y equal to 0. So what happens means these molecules are in close contact with the plate surface. Since they are in close contact, there will be a strong friction. Between plate surface and fluid molecules. And which makes the problem at y equal to 0 as a relative velocity between fluid molecules and the plate molecules will be 0. Let me repeat once again. Because of having a strong friction between fluid molecules and the plate molecules, there will be a relative velocity between fluid molecules and the plate molecules is equal to 0. Relative velocity. I am talking about relative, not individual velocities. Relative velocity means velocity of your fluid minus your plate, that has to become 0. So technically we call that concept in fluid mechanics as no slip boundary condition. So please be careful. This kind of boundary condition is only valid at the surface of your plate. Where your fluid and the surface is in contact. That is technically called as no slip boundary condition. What does that mean? Means the relative velocity between fluid and the plate has to become 0. The name itself tells you no slip. There is no slip by the fluid over the surface. It is almost at rest. They are moving at the same velocity. So that's the meaning of no slip boundary condition. That happens only at y equal to 0. This happens only at y equal to 0 because that is the location where your fluid molecules and the plate molecules are in direct contact. When you go to the next layer, when you go to the second layer, suppose say, I'll choose layer number 2. When you go to the second layer, so what happens? This layer is not in direct contact, right? This layer of the fluid is not in direct contact. So what you expect here is this layer will have some value of velocity. The second layer will have some value of velocity. which is little higher than your first layer, which is little higher than your first layer, but not like very large change you will see. Very large change you will see. This have a velocity which is little higher than your zero value. Say let us assume that you have a value of u which is little higher than zero, which is close to zero suppose. But the first layer will have zero value. Is it clear? So what you can expect now when you go to the next layers, slowly in the y direction, what do you expect is the values of velocities, will be increasing, At a particular value of y, those values of velocities should reach to the upstream boundary condition, which is u infinity, So that means physically, if I draw a plot here, say at a given x, I want to draw the velocity distribution, how it is varying with y. So we know at y equal to 0, u is 0, this point is fixed. And at a far y from the plate surface in the perpendicular direction, we know this value of velocity is u infinity. Is it right? And these two has to be connected. Is it correct, everybody? Understood? Because from here to here, your value of velocity is varying in some trend, maybe linear variation, maybe parabolic, maybe cubic, whatever maybe. Some variation is there. Let me connect with some curve. Don't bother about what kind of variation it is, but there is a variation. Since velocity is vector, I can give both magnitude and direction here. But after this y, we will not see any change in velocity. Is it right, everybody? After this y, we will not see any change in velocity, which is at every y you will see the same value, which is u infinity. And this is the value of y up to which you will see a change. And we'll try to represent this value of y with some value called as delta. So basically speaking, this is what is a fluid mechanics problem that you have learned in your fluid mechanics subject, which is a topic called the boundary layer, What it tells is a total flow over a surface is divided into two parts. One close to the surface, solid surface, one very away from the surface. So what it does is, close to the surface, you will see velocity variation. Technically, mathematically speaking, that is called as velocity gradient. Velocity gradient means velocity is changing with respect to position. Whereas very away from the surface, that means say y greater than delta, you will not see a velocity variation. That means the velocity gradients are zero. That means basically speaking, at every x we will be having two problems. One is a problem associated with velocity gradient. The other problem, no velocity gradients. So if you join all these kind of points, wherever you see a delta at different x, suppose here you will see x somewhere here. If you try to join all these points, this will come out as something like this. And these are region inside which you will see velocity gradient. Outside this region, you will not see any velocity gradient at every x. Fine, clear? And this is what is technically called as boundary layer. In this particular chapter, we call this as hydrodynamic boundary layer. And this delta, whatever you have taken here, is given with a name called as boundary layer thickness. And this layer is called as hydrodynamic boundary layer. Everybody clear with the fluid mechanics problem? Any doubt in how to differentiate these two regions and all? Any doubt anywhere? Right? Clear? So with this understanding, let us go to the next part of a problem, which is our temperature effects. That means That means you are having a condition now, suppose a T infinity which is different from Ts, T infinity which is different from Ts. Let us assume a simple problem where you are having say Ts greater than T infinity. Because you want to study heat transfer, you should give a condition in terms of difference in temperature. So therefore, I am picking a condition where your Ts, the temperature of the surface, plate surface, is greater than your free stream fluid. So basically speaking, you want to cool down the surface by flowing some fluid with some temperature which is less than your plate temperature. That's a problem here. Are you guys clear? You want to cool down the surface. You want to cool down the surface by bringing in some fluid with some velocity whose temperature is less than your plate temperature. Less than your plate temperature. Is it clear again? Everybody understood? So that's the extra complication you are adding to the existing problem. Already the problem got existed in your fluid mechanics, which is shown like this. Already this is happening. On the top of that, you are adding the temperature effects. So therefore, at any x, if you see, let me change the color. At any x, if you see, suppose I'll sit here, then x. So if you draw the temperature distribution, so we know very clearly the free stream temperature T infinity is less than your plate temperature. So please be careful. This need not be always. You can have the other case also. What is that? Ts less than T infinity also. Don't take like every time you want to cool down the fluid. You can have a problem where you want to heat the fluid also. Heat the fluid also instead of cooling. Okay, so now very close to surface for this condition, Ts greater than T infinity, very close to surface, you will have a higher temperature. That means a higher magnitude. Is it right? Whereas far away, you will be having a lower magnitude. So these are the points to be connected. Are you guys following? Everybody understood? Far away, you have a lower temperature because your T infinity is less than Ts or Ts greater than T infinity, both are same. And you want to join these 2 points. And this is a temperature field. You are not talking about velocity, you are talking about temperature, which is a scalar. Temperature is a scalar. Only magnitude is enough. No need of direction, like your velocity. Velocity needs a direction apart from magnitude. So this is a temperature, no need of direction, you need only magnitude. So when you are moving from a plate to the top, you will see a reduction in temperature. You will see some reduction in temperature, and these will be joined by means of some curve. And after this location, we will not see any change at all. It is constant. This is what is T. And this is your plate temperature, Ts. Just for understanding purpose, let me redraw here. This is how it looks. I'm just taking out the plot what I have drawn. This is what is T infinity. This is Ts. And this is what is T function of y. Right, clear? And this is what is U function of y, similar to T function of y. Clear? So basically what is happening here is a heat is entering into the fluid in the y direction. Is it correct? Some amount of heat is entering into the fluid in the y direction. At y equal to 0. So that will be taken out. Because of having some bulk motion. So here the bulk motion means you are giving some velocity to the fluid. So that fluid temperature is less than your plate temperature. So because of the difference in temperature, a fluid comes in with very high velocity, takes that heat and goes out. Let me repeat once again. At any x, some heat is coming into the fluid in the y direction. Right? And to take that heat out, some fluid is sending from left to right. Some fluid is sending from left to right with a velocity of V infinity. That is technically called as with bulk motion. And the temperature lower than your plate temperature. So this comes into that region where you are pumping in the heat, takes that heat and goes out. Takes that heat and goes out. So these kind of things will be repeated and repeated in reality. That's why these are called as open system problems in your fluid mechanics and your thermodynamics. So open system means we'll be having both mass transfer as well as energy transfer. Right? Correct, everybody? You will be continuously flowing with some velocity and continuously you are pumping in some energy. So it comes in, takes energy and goes out. Comes in, takes energy and goes out. And both your mass as well as energy is flowing in and flowing out. So that's why these are called as open system problems. Open system problems. So now let us see what's the difference between what you have learned earlier and what you are learning now. In the earlier case, you didn't talk about you didn't talk about U infinity term in the earlier discussion of conduction. Nowhere you talked about velocity. Whereas this is the problem where you are seeing a bulk motion. And so therefore heat transfer with the bulk motion is called as convection. Heat transfer with the bulk motion is called as convection. Is it right? Shall I keep something like that? A statement? Heat transfer with the bulk motion is called as convection. So similar to your velocity effects, you can see the temperature effects also in terms of boundary layer. Let me choose some kind of curve here, which is passing through this point. So similar to hydrodynamic boundary layer, you will be having thermal boundary layer, and this value of delta up to which you will see the changes of temperature. Let me keep here to avoid confusion. The value of y up to which you will see the changes of temperature at a given x called as delta T, which is technically called as again thermal boundary layer thickness. Just to differentiate from your fluid mechanics concepts, we are adding a term called thermal. That's it. Thermal boundary layer thickness. Thermal boundary layer thickness. You can have all the possible cases. What are the possible cases means? You can have delta greater than delta T. We'll see all these things later. We can have delta equal to delta T. We can have delta less than delta T also. All the three are possible in reality. When occurs at what time means, we will see the situations later. All the three cases are possible. The one what I have drawn is delta greater than delta T. You can have delta less than delta T also. You can have both matching also. There is nothing wrong. We will see why nothing wrong later. But what the conclusion from this problem means? Heat transfer with bulk motion. Is called as convection. Heat transfer with bulk motion is called as convection. Is it right? Clear, everybody? So locally, if you see, the first layer of the molecule is at rest, right? The first layer of the molecules are at rest. So what do you understand from the first layer? Anybody? A first layer which is at rest. Anybody? First layer of the molecules are at rest. Huh?
The temperature of the
More
plate as well
resistance.
as that first layer will be
What?
the temperature of the plate as well as the first layer will be equal temperature.
First layer temperature, plate temperature. No, I'm expecting something different. Anybody else? What you're expecting at the first layer because of molecules at rest?
Kokoshi forces some resistance.
No. Please try to understand what is happening in the first layer.
Conduction.
What?
There is no bulk motion. It is a conduction, sir.
Very good, very good. Exactly. So the first layer is not having any bulk motion, right? Yes, sir. Physically, that is what you are seeing in the problem. The first layer is not having any bulk motion. So what you expect in the first layer is conduction. What you expect in the first layer is conduction. So that should be taken as convection because of bulk motion in the next layers. Are you guys clear what I am telling you? The first layer is not having any bulk motion. So whatever heat has conducted at y equal to 0 in the fluid. Is it right, everybody? Is the statement clear? Because of no bulk motion at y equal to 0 should be convected. Please try to understand. These are the things where students make a lot of maybe confusion, or because of confusion what they will do, mistakes. So that's where you have to understand the physics. The first layer is not having any bulk motion, whereas the remaining layers are having bulk motion. So therefore remaining layers, whatever you are having a heat transfer, that is convection. Whereas the first layer of the molecule and the plate, they are completely with conduction. They are completely with conduction. So therefore, convection is not a primary mode of heat transfer. Convection is not a primary mode of heat transfer. Conduction is a primary mode, and that will be followed by convection always. Without conduction, we will not see much about convection. Are you guys clear, everybody? So that's why we always talk about conduction first. Then after learning conduction properly and completely, then we'll go for convection, because conduction is always a primary mode of heat transfer. The convection is a secondary mode. Convection is a secondary mode. So that's why, technically speaking, what some textbooks they prefer in defining convection is, conduction plus, what you'll write? Come on, speak out. Convection is defined as conduction plus, come on, conduction plus bulk motion. Is it right? You have a conduction in the y direction. You have a conduction in the y direction that have to be added to bulk motion. This added value will come out as convection. This is what is bulk motion. Or the other wordings, I mean, these are all different kinds of words people give. Conduction is also called as diffusion, we know. Just now we have defined. And the bulk motion is called as advection. Bulk motion is also called as advection. So diffusion plus advection is called as convection. Diffusion plus advection is called as convection. Diffusion plus convection is called as diffusion plus advection is called as convection. Everybody clear? Any doubt? And this kind of convection, whatever you have seen, is called as forced convection. Is called as, please be careful with the wordings, forced convection, because you are forcing the heat transfer to happen by sending or pumping in a fluid with some velocity, by using some kind of blower or fan, or by spending some kind of work input in the upstream. Is it right? Fluid will not flow automatically, right, with some velocity of u infinity. You need to spend some work. We need to apply some force on the fluid so that the fluid will be set into some velocity of u infinity. So that's why this is what is called as forced convection. That's why this is called as forced convection. So there is something like free convection or natural convection, which we'll see in the next class, because just 2-3 minutes are left, which we'll see in the next class. And we didn't yet not discussed about the governing law, that also we will see in the next class. So any queries that you want to discuss? Anywhere, any questions? So please be careful. Convection is not a primary mode of heat transfer. It's a derived, secondary mode of heat transfer. A primary is your conduction or diffusion. So that's why we always talk about conduction as a first chapter. Then we jump into convection in the second chapter. Is it clear, everybody? So if you have any queries, you can discuss now. We have some 3 to 4 minutes. We can discuss that. Otherwise, we'll meet in the next session.
Sir,
Yes.
sir, what about the thermal boundary layer in terms of conduction, sir?
In terms of conduction, will not. That's what boundary layers and all is coming in the fluid. Whenever you have a gradient and all, whenever you have a velocity, there only we talk about boundary layers. We don't talk about this kind of boundary layers and all when you don't have a bulk motion. When you, especially speaking, they are talked in fluids, not in solids.
Okay.
Boundary layer concept is completely for fluids, not for solids. Any other questions? So things are fine. Everybody is following the things, or do you want to make me to recorrect some things in terms of say presenting, in terms of say talking, or whatever maybe? Clear? Okay. Thank you. We'll meet in the next session based on our schedule. Fine. See you.
Thanks.
Thank you.
Bye.
Thank you.
Thank you,
Yes.
sir.
Welcome.